In this video, we're going to talk about molecular orbital theory. So let's use hydrogen as an example. Hydrogen has one valence electron, and if we mix two hydrogen atoms together, these two will combine and form the hydrogen molecule, which you can also represent like this. Now, each of these hydrogen atoms has an 1s orbital in which one electron is placed. Let's call this hydrogen A and hydrogen B. So this is 1s-A and 1s-B. Now when these two atomic orbitals are mixed, they combine and form two molecular orbitals. The number of orbitals is always conserved. So if you're combining 4 atomic orbitals, 4 molecular orbitals will be produced. Now you got to think of electrons as waves. Let's say if you have two waves that are in phase with each other. What's going to happen when you add these two waves? They will create a larger wave. Constructive interference will occur. Now if you think of electrons as waves, if two atoms contain electrons that are in phase with each other, they will combine and form a bonded molecular orbital. So let's say this is the 1s-A orbital and this is the 1s-B orbital. So these two are in phase. So if we add them, this will produce a bonded molecular orbital. So in the bonded molecular orbital, let's call it MO1. This represents a region of a high probability of finding an electron. And the electron will most likely be located in between the nuclei. Because if you think about it, if you look at the HH molecule, the electrons are between the two hydrogen atoms. And so whenever the electrons are in this region between the nuclei, it favors the formation of a molecule. So let's say that these two circles represents the nucleus of each hydrogen atom. So that's a positive charge, not a positive sign. Well, it is a positive sign, but it's not the same as this positive sign, where that represents a numerical sign. This is actually the charge of the nucleus. And we're going to place the electrons between the two nuclei as represented by the electrons in this bond. Now this proton, the hydrogen atom has one proton in its nucleus. That proton is attracted to the first electron in front of it. So it feels a force that's going to push the nucleus of the hydrogen atom towards the right. And keep in mind, the majority of the mass of the atom is in the nucleus. Now this proton is also attracted to this electron. So there's another force that pulls it towards the right. Now this proton is repelled by this proton, but that proton is further away compared to these electrons. So the electrostatic force will be reduced because of the increased distance. Now the same is true for this proton. It's attracted to these two electrons, but it's repelled by the other proton. And so the net force for a molecule in this arrangement is an attractive force. Notice that you have more forces causing the protons to move together rather than the ones that are pulling apart. So with reference to the protons only, there's 4 forces that wants to bring the two hydrogen atoms together. And there's 2 of them that wants to pull them apart. So this setup, when the electrons are between the nuclei of the hydrogen atoms, it favors bond formation. It favors the formation of a molecule. And so that's the situation that we have in this bonded molecular orbital. The electrons are between the nuclei. Now what happens if we have 2 waves that are out of phase? So let's say this is positive, that's above the x-axis, and this part is negative. Well, if you add positive 5 and negative 5, they will cancel out, they'll add up to 0. So destructive interference will occur. So you can treat the electrons as waves. So the electron in the first hydrogen atom, we're going to give it a positive sign, and the second one a negative sign. So if we add these two, destructive interference will occur. And so what's going to happen is we're going to get an antibonding molecular orbital. So this is going to be positive and this is negative. So notice that there's nothing in this region. So this region is known as a node. A node is a region where you're least likely to find an electron at that region. The probability of finding an electron at a node is basically 0. So let's say if these are two hydrogen atoms, then for an antibonding molecular orbital, we should not place the electrons in between those two hydrogen atoms. Rather, they should be on opposite sides. So that's just a visual representation of an antibonding molecular orbital. So this type of orbital does not favor the formation of an H2 molecule. So let's say if we were to draw the charges. Let's say this is the positive charge of the nucleus of the two hydrogen atoms. So this time the electrons, they're more likely to be found outside of the region between the nuclei. So you probably find it on the left side or on the right side. So analyzing the forces that are present in this situation, we can see that it's not going to favor bond formation. Let's focus on the protons. So this proton is attracted to the electron on the left. Now it's repelled by this proton, but it's attracted to this electron, but that electron is far away. So that force of attraction is going to be weak compared to these forces that want to repel it from the other hydrogen molecule. So the same is true for the other proton. So notice that we have 4 large forces that want to cause these two hydrogen atoms to move apart from each other. And there's only 2 small forces that want to bring the nucleus together. So therefore, the net force in this situation is repulsive. The hydrogen atoms do not want to bond in this situation. So let's see if I can visually summarize what we just talked about. So let's compare the bonding molecular orbital to the antibonding molecular orbital. So in the bonding molecular orbital, the electrons can be found in between the nuclei of the hydrogen atoms. So there's a high probability of finding the electrons there. In the antibonding molecular orbital, the probability of finding an electron between the nuclei is very low. You're more likely to find it outside of the nuclei. When I mean outside of this region. So it's going to be on either side between the nuclei. So now, the bonding molecular orbital has a wave that looks like this. And the antibonding molecular orbital has a wave that looks like this. So antibonding is associated with destructive interference, and the bonding molecular orbital is associated with constructive interference. So let's say this is the nuclei of the hydrogen atoms. So here you're more likely to find the electrons in this region. So drawing the electron as a wave, the electron is going to be more likely in this region. Now let's say if these are the nuclei of the hydrogen atoms, you're more likely to find the electrons outside of the nuclei as opposed to in between the nuclei. So keep in mind, for the bonding molecular orbital, the net force is inward, it's basically an attractive force. It brings the hydrogen molecules together, favoring bond formation. For antibonding, the net force is repulsive. It repels the hydrogen molecules away from each other, favoring antibonding, or the opposite of bonding. Now let's talk about the energy diagram of a molecular orbital. So we're going to combine the 1s orbital of hydrogen A with the 1s orbital of hydrogen B. When these two atoms get together, they will create the H2 molecule. And so if we're combining two atomic orbitals, two molecular orbitals will be produced. The one that's lower in energy is going to be the bonding molecular orbital. And one that is higher in energy is the antibonding molecular orbital. Now this is also known as sigma 1s, and this is sigma 1s star. Whenever you see the asterisk next to it, it represents a high energy antibonding molecular orbital. Keep in mind a sigma bond is formed for the head-on overlap of atomic orbitals. So each hydrogen atom brings one electron with it. Now, in order for the electron to jump to a higher energy level, you got to put in energy to it. However, natural systems tend to seek the lowest energy state possible. So it's easier to fall to a lower energy level than to jump up to a higher energy level. It's easier to come down a mountain rather than to climb a mountain. So these electrons will naturally fall to the lower energy level. And whenever an electron falls from a high energy level to a low energy level, energy is released. And this is consistent with bond formation. Whenever two atoms combine to form a bond, it's an exothermic process. Energy is released. It takes energy to break a bond. Breaking a bond is an endothermic process, but to form a bond, energy is released whenever that happens. So as these electrons fall to a lower energy level, they will release energy, which favors bond formation. Now here's a question for you. The hydrogen gas molecule, would you expect it to be paramagnetic or diamagnetic? Paramagnetism is associated with unpaired electrons. Diamagnetism is associated with paired electrons. So for any molecule that has unpaired electrons, it's going to be paramagnetic. If it only has paired electrons, it's diamagnetic. So hydrogen gas only has paired electrons. So therefore, we should expect that that substance should be diamagnetic as opposed to paramagnetic. So what does it mean for a substance to be paramagnetic? A paramagnetic substance is one that is attracted to an inducing magnetic field. A diamagnetic substance is one that is repelled by an inducing magnetic field. So hydrogen will be repelled by it. Now the next thing that you need to be able to do is you need to know how to calculate the bond order of the H2 molecule. So to calculate the bond order, I'm going to write BO for bond order. It's equal to the number of bonding electrons minus the number of antibonding electrons divided by 2. So this is the bonding molecular orbital. So there are two bonding electrons. This is the antibonding molecular orbital. So there's 0 antibonding electrons. So 2 divided by 2 is 1. So the bond order of H2 is 1. A bond order of 1 usually correlates to a single bond. A bond order of 2 typically correlates to a double bond. And a bond order of 3 usually correlates to a triple bond. This is not always the case, but for the most part, I've seen this to be true for many examples. And for this example, notice that hydrogen has a single bond, which is consistent with a bond order of 1. So as the bond order increases, the stability of the bond increases, which means that it's lower in energy. A molecule that has low energy is a molecule that is stable. A molecule that has high energy is one that's reactive, it's not stable. So energy and stability are inversely related. As the bond order increases, the bond length typically decreases. Stronger bonds tend to be shorter, and longer bonds tend to be weaker. Consider the nitrogen molecule. It has a triple bond, and as a result, it's very stable. It's hard to cause a nitrogen molecule to participate in a reaction. It's extremely stable. And this molecule has a bond order of 3. And triple bonds tend to be a lot shorter than single bonds. So it's harder to break a triple bond because there's 3 bonds holding the nitrogen atom as opposed to 1 bond. So think of this illustration. It's a lot easier to break 1 pencil than to break 3 pencils. So it's harder to break 3 pencils. The more pencils you have, the greater the strength. But it's easy to break 1 pencil. So single bonds are easier to break than a triple bond. Oxygen has a double bond at its center. And so the bond order for the oxygen molecule, if you draw the molecular orbital diagram, you'll see that it's equal to 2. And fluorine, which has a single bond, has a bond order of 1. So nitrogen gas is the most stable molecule out of everything that's listed. Fluorine is the least stable. In fact, fluorine is one of the most reactive elements in the periodic table. So it's very reactive. Nitrogen gas is the least reactive. It doesn't want to react, it's stable. Oxygen is somewhere in between. Typically, oxygen is reactive, but you got to get it started. For example, let's say if you have gasoline laying on the floor. That gasoline will not react with oxygen unless you ignite it with a spark. And once you ignite it, a lot of energy will be released. But it takes a spark to break that bond. And once you break it, then a chain of events will be unleashed and a lot of energy will be released. But for the most part, that bond is pretty stable. And you got to put in energy to get that reaction going. So oxygen is somewhat reactive. It's not as reactive as fluorine, but it's more reactive than nitrogen gas. So what you need to know is that the higher the bond order, the more stable the molecule is, and the less reactive it tends to be. A molecule with a low bond order tends to be more reactive and less stable. And also, it tends to be longer in bond length compared to one with a higher bond order. Now, let's look at another example. Let's draw the molecular orbital diagram for the H2- ion. So what I want you to do is determine the bond order and also write the electron configuration. So let's say this is 1sa, 1sp, and this is going to be sigma 1s and sigma 1s star. So now let's say this is the hydrogen atom and this is a hydrogen ion. When we add these two, we can get the H2 ion. So hydrogen A has only 1 electron. Hydrogen B has 2. So first, according to the Aufbau principle, we got to fill up the lower energy levels first before we fill up the higher energy levels. So the molecular orbital diagram looks like this. So in order to calculate the bond order, it's going to be the number of bonding electrons, which is 2, minus the number of anti-bonding electrons, which is 1, divided by 2. So 2 minus 1 is 1. So the bond order is 1/2, which means it's less stable than H2, which had a bond order of 1. But this molecule could exist because the bond order is not 0. So it's somewhat stable, but not very stable. Now the electron configuration for this molecular ion, it's going to be sigma 1s. There's 2 electrons in that orbital. And then sigma 1s star, which has only 1 electron. So this is the electron configuration for the molecular ion H2 minus. Now what about the dihelium atom? Is it stable? Does it exist? Well, let's find out. So helium has 2 electrons in its 1s orbital. And so since we're combining 2 atomic orbitals, 2 molecular orbitals will be created. So this is going to be completely filled. Therefore, this substance is diamagnetic because it only contains paired electrons. H2 minus had 1 unpaired electron, which makes it paramagnetic. Now let's calculate the bond order of this molecule. So we have 2 electrons in the bonded molecular orbital and 2 in the anti-bonded molecular orbital. And we're supposed to divide it by 2, not 0. 2 minus 2 is 0, and 0 divided by 2 is 0. So a bond order of 0 means that there is no bond. This molecule does not exist. It's not stable. And helium gas exists as individual helium atoms, not as diatomic molecules. The electron configuration for this molecule is going to be sigma 1s with 2 electrons and sigma 1s star with 2 electrons. So that's how you can write the electron configuration for that substance, even though it doesn't exist.